Hello there. In this video we're going to look at quadratic functions. Up to now the functions that we've dealt with have all been linear, which means that if we were to represent them, to draw them on the Cartesian plane, an xy axis, that they would look like a straight line. Today we're going to look at some other shapes. A quadratic function, when plotted, it looks like a curve. Let's start off by looking at what do these functions look like in equation form. Well, a quadratic function, and again we would use the same labels that we've come to know, which are typical to represent functions, mainly the most common being f. But we could also have g, we could have h, we could have any particular letter, but f, g and h are the ones that most commonly occur. So a quadratic function f in x. Now remember that simply means x. We're going to use x for our inputs. So our inputs will change. We will have several inputs. So therefore we're going to use x when we're not particularly focusing on one at any particular time. Now a quadratic function has an x squared term. In other words, it looks something like this. The f of x is still the same. Now remember, f of x can also be represented with a y, and that simply means that the outputs, a function where we put inputs into it, we obtain the outputs, we get the answers by performing this calculation, the rule of the function. The operation that we have to do on the input to get the output. And as you can see, we have an x squared. The input has to be squared. Now the letters A, B and C simply are for any particular number. So different functions will have different numbers here in those three places. So remember that when we have a number is not a letter. So it's not a variable, it doesn't change, and therefore we call them constants. And note that we cannot have the constant 0 for a. In other words, we can't have 0 lots of x squared, because if you have 0 lots of something, then that means we don't have anything at all. So the only part of the function would be bx plus c, which, if you recall, this is what a linear function looks like. When we multiply the input by something, b, and then add a constant. Now, of course, that constant could be a negative, so we might be minusing a number. So you'll see that the quadratic function then is just one extra calculation than what the linear function was. This is the linear function, but we also have to do something else first. So we are squaring, remember that means to multiply by itself the input, multiplying that answer then by a constant, whatever is in front or attached to the x squared. Then we will have to add to that our input times by whatever our b constant represents, and then we will have to add our c. So the graph of a quadratic function doesn't look like a line, it is a curve, and we call this curve a parabola or a parabolic curve. Now the graph of the curve, a parabola, can either be, this looks like an N, but I like to call it like a frown. So if you pretend that this is a mouth, it's not a very happy one. Or it could be a smile, like a U shape. And that will all depend on the coefficient of the squared variable. Now, if you remember, coefficient means the number attached to the letter. And the squared variable means this term here. This term is the variable, the letter x, that's squared. So in other words, whatever number a is, whatever number is attached to the x squared in front of the x squared, that will tell us whether our shape is going to be a frown or a smile. So for example, here is what we call a positive quadratic function. It's a smile. And that's why it's quite helpful to think of it as a smile or a frown, because you smile if you're positive, if you're feeling quite happy. Now, this is what an example then of a quadratic function will look like. Notice that the letter that's squared, so x squared, has a number in front of it, the coefficient is positive. It's the number 3. So if this number is positive, then our graph will look like a smile, like a U shape. Now, alternatively, if we look at this function, we have a negative number, a -2, for example, in front of the x squared, attached to the x squared. So the coefficient is negative, and that helps us to understand that our quadratic function will be a frown. It will be an upside down curve. Very important point. It's very important to note that a graph of a quadratic function, so we know that it will be a quadratic if there's an x squared. It will always be a curve. And because of that, we cannot just plot 3 points like we learned to do with the linear functions. We learned that a line only needs 2 points, but we plot a third to make sure that we're correct. But when we have a quadratic function, so the rule of the function has an x squared, the input has to be squared, then we have to plot all the values for our domain. Now remember, the domain is a keyword that means the set of all the inputs. So whatever the inputs are, we can't pick the smallest, the largest, and one in the middle. We have to actually work out the couples for all of our inputs, and then we have to plot all of those couples onto our graph in order for it to be correct. So let's have a look at an example. So this is what a question might look like in an exam. First of all, it asks us to complete the input-output table below. And as you can see, we've become quite familiar with these. There's always 3 columns. The first column is for the inputs, x. Then we have a larger middle column, and that's for all our calculations, our workings. It's where we put the right-hand side of the function, and we change then the x depending on which input we are calculating the output for. So the one that's been given for us, we are interested in the input 0. So in each of the places where x belongs in the functions rule, the right-hand side of the equation, we're changing the x to that number. So you'll notice that the only thing different about this line to the function's actual rule, the question, is that instead of the x, we now have the number 0 because we're working out the output for the input 0. Now remember that when we substitute values for a letter, that means we swap the letter for a number, that we always put it in a bracket, because that helps us to remember. For example, this bit here is -6 times x. It's -6 lots of x. It's not -60. So by putting a bracket when we've swapped the x for the 0, it helps us to remember that we must multiply here. And likewise, that this is the input, so in this case 0, that has to be squared. So for this particular function, every input is going to be times by itself, and then we're going to take away from that 6 lots of that input, and then add the number 8 to get our output, which is our third and final column. Remember, f of x can also be called y. When we plot our points later, we'll be plotting the x with the y as each set of points or each couple. So let's check these calculations so we understand where this 8 has come from. We start off by applying our indices. Remember with BIMDAS, when we have more than one sum to do, we've got a square, we've got a minus, we've got multiplication and addition. So we need to do it in the correct order. So in our BIMDAS or BOMDAS or PEMDAS, whichever you have learnt, we know that we apply the squaring first. So 0 times itself, 0 squared. 0 times 0 gives the answer 0. Then we have minus 6 times 0. Well, again, anything times 0 still makes 0, 0. So we've got 0, take away 0, we're still on 0, and then we have to add 8, which gives us the answer 8. So we are expected then to complete the rest of the input-output table. So each time we're going to be changing the numbers that appear in the brackets here, where the X was, to these numbers down the side, the different inputs. So let's have a go at that. So as you can see, everything stays the same as above, except the number inside the brackets, where the X was in our rule, changes to the input that's to the left of it. And then we must work out our answers to get our outputs. It's really important that we show as many calculations of full workings as possible. So for quadratics, I would recommend that you have a couple of lines for each of your input and outputs to help you with the workings in this second middle column. So let's find out the outputs for each of these inputs. Let's work out the output for 1. When the input is 1, 1 times itself, 1 squared, becomes 1. Then we have to take away from that 6 times 1. 6 times 1 is 6. So 1 take away 6 is minus 5. And then we add 8 and we get the answer 3. And you'll see that we have the same calculations each time, and these are the different answers. We'll pick one more to go through. Let's pick the input 3. 3 squared means 3 times 3, which is 9. 6 times 3 is 18, so 9 take away 18 is minus 9, and then we add 8 to that, and that's how we got the answer minus 1. So we haven't just picked a smallest input, the largest, and one in between. We have worked out all the outputs for every single whole number value in the domain, the full set of inputs. Now, just like we did with the linear functions then, we will have to then list the couples of the function. The couples, which we know are also called the ordered pairs, are simply all the inputs with their unique outputs together in a set of curly brackets. So here we have our curly brackets, and we have the first input together with that output, and each in their own little bracket. And each pair is separated by another couple. So all of the first numbers in these brackets are the first numbers in our input-output table, the inputs, the numbers under X. And all the second numbers are all the outputs, the numbers in the third column, the outputs. So let's just double check that we know where this point has come from, this couple, this pair. It's when the input is 4, so here, then the output when input is 4 is 0. Once we have got our couples and ordered pairs, and remember that we get marks for each of these stages, lots of marks for our input-output table, marks for our couples, we can then start to plot those couples onto our coordinate plane. And just as we did before, we have to try to make the best use of the space that we've been given, and we have to carefully pick our axes, the size of our X and Y, based on the numbers from our couples. As you can see, most of them are positive, but we do have a Y coordinate that's negative here. Remember, the first numbers are X's and the second are Y. So we know that our X axis is only positive numbers, all the numbers from 0 to 6. So we could simply just have all the positives from 0 to 10 maybe. Or you might decide that you would like a little bit of space to the left and draw from -1 up to a little bit of space to the right, up to maybe the number 7. And then our y-axes, our outputs, the biggest number is 8 and the smallest is -1. So I might draw it from maybe -2 down here up to maybe 10. So, as you can see, here is our scale. We know that we have to do a little bit of a negative on the y-axis, but we don't have to have anything negative on the x-axis. Once we've got our scale drawn, our Cartesian plane, and remember to use a sharp pencil and to use the squares and the lines in your book or the exam paper, and then to write your numbers in pen. We need little markers as well to show exactly where those numbers are, and the same distance in between each number on the same one axis. So if there's one box between all the numbers on this side of the x-axis, there has to be one box between all the numbers on this side. So let's start plotting our numbers. So if we look at our first couple, it's the coordinate 0, 8. 0 on the x-axis, 8 on the y. X comes before y in the alphabet. So here's 0 on the x. Remember, x is across, y is up and down, like the tail in a y goes up and down. So 0 for x and 8 for y. It's this point here. Now, again, like with the linear function, we do have to label each of these points, but I would leave it until you have finished drawing your curve so that you don't write over the pencil drawn curve, making it harder to read. The second point then is 1, 3. So from 0, we move 1 to the 1 on the x-axis, and then 3 is positive, so that's going up to the 3 on the y-axis, and it's this point here. Next point is 2, 0. So again, from 0, we move 2 spaces to the positive direction for x, and we don't move anywhere at all for the y, so it's this point here. Our next point is 3, -1. So 3 on the x, -1 on the y. Here's our point. 4, 0, level with 4 on the x and 0 on the y, so it's here. 5, 3, 5 on the x, +3 on the y, and we go up here. And then the last one is 6 on the x and up to 8 on the y. Now have a look at these points. Do you notice something? Maybe you notice that they're symmetrical, that they're opposite each other. Well, in the ordinary level course, this will always be the case in your exam, which really helps in case you have one point that might be, say, over here, which really looks out of place, because all of these curves will be smooth smiles or frowns. There won't be any jagged or squiggly lines. And there's a lot of marks going for drawing them really neatly and accurately, which does take a bit of practice. So we will be practicing a lot of these. Now the only thing left to do then is, once we've plotted those couples, is use these points to graph the function. And here we have the function again, which is y equals x squared minus 6x plus 8. And we knew it was a parabola because the x is squared. And we know that y is the same as f of x. And we know that the domain is all the values of x from 0 to 6. Now, of course, that means the inputs range from the number to the left to the number to the right. Now, you'll notice that there is a little bit of a mistake on this typing, but it should have a little or equals to underneath if we are still wanting to have those points 0 and 6 included. Okay, now remember the bit after the comma simply means that x belongs to the real number set, which means x is everything that we've studied it. It's all the real numbers. Now, this part here sounds quite confusing, but all it's actually asking us to do is, once you've plotted your points, is to connect them all with your very smooth pencil-drawn curve. Now, drawing with pencil, even for exercises and practice, is extremely important because this is one of the types of questions where you might decide that you haven't drawn that quite right because they have to be done freehand, no rulers or straight edges whatsoever. And it's actually quite tricky to try and do that, especially if there's a big space. Now notice if these are level with each other, then we have one in the middle down the bottom here. Now that is exactly halfway between this point and this point. And that means that this is the very lowest point of our parabola. The examiner will be looking to check that this is where your curve meets at the bottom, that you do not go underneath, and that it absolutely touches this point and then starts to rise back up to the next point. So let's have a look at that like this. So you're going to make sure that every point has your pencil curve exactly going through it. They'll be checking each of the points to see that your pencil curve does smoothly go through those points. Sometimes practicing a little bit of feathering gently with your pencil very lightly, so that if it goes wrong you can cross it out, and when you find the really correct pattern that you're happy with, that's nice and smooth, then you can go over it a little bit harder and rub out any of the bits that you don't want. And in the next video I'll be demonstrating how you can do this. Now you might be asked certain questions. Notice that we discussed that 3 minus 1 is the lowest point of the curve. Now that means that it's the function's minimum point. If this function had been negative, so it was a frown rather than a smile, then we wouldn't have a minimum point, we would have a maximum. It would curve up and up until it got to a maximum point, and then it would curve back down again. One last thing before you go. How can the number 7 change to even number? 7 cannot be divided by 2. Why, it's easy, of course. Just remove the S from the front. 7, even. Thanks for listening, and I'll see you in the next video.